Hello everyone, I wanted to go over this problem that I saw a video on just a little while ago, and this is the integral from 0 to pi over 2 of x over tangent of x. I actually saw this in a black pen red pen video, which I'll actually link in the description below, but the way I'm going to show is a little bit different. In fact, reading through the comments, it seems like a few people actually did it the way I'm about to present right now. So the first thing is to rewrite this as x times the reciprocal of tangent, which of course is cotangent. And then we'll do, of course, integration by parts. Now, if you set up integration by parts in kind of the usual way, u will be equal to x, so the du is dx, and the dv, which I'll write below actually, there we go, dv, is cotangent of x. Now, if you don't know, the antiderivative of cotangent is actually ln of sine. It's not very hard to see that. That's because derivative of ln of sine, of course, is the derivative of the inside, which is cosine over the original inside, which is sine. So cosine over sine is indeed cotangent. I'm missing a dx there. Now, by the integration by parts formula, this is uv minus the integral of v times du. So that means this will be equal to uv times, or uv is x ln of sine, but then, of course, evaluated between the limits, and then now minus the integral, scoot this over a bit, from 0 to pi over 2 of v du, which is, of course, just ln of sine of x dx. Now, I've actually seen quite a few people do videos on this, but I think I've seen with cosine instead of sine in the inside. But in any event, I'll actually show this in kind of a neat way. I don't know if this is quite the way I've seen it done before. But before we get to that, let's take care of this, because this is actually quite interesting. So when x is pi over 2, sine of pi over 2 is 1, ln of 1 is 0, so the whole thing becomes pi over 2 times 0, which is 0. So that's interesting. So we have this 0 minus. Now when you plug in 0, I'm going to do this in green below. You'll get 0 times ln of sine of 0, which is 0. But ln of 0 is negative infinity. So this is an indeterminate form, of course. And I'll reciprocate x to make that the case. So the limit as x goes to 0 of x ln of sine of x can be rewritten as a limit as x goes to 0 of ln of sine of x over the reciprocal of x. And this is, of course, of infinity over infinity form, so by L'Hopital's rule, we can say this, the limit as x goes to 0 of derivative of the top, which we know is cotangent from previous discussion, over negative 1 over x squared. Now, if you rewrite this, this is just, well, reciprocate the bottom to get negative x squared on the top, and then cotangent reciprocated down below is just tangent. So that's kind of interesting. We're still in the limit, of course. But now when you plug this in, you get 0 over 0, which is, again, indeterminate form. So finally, by L'Hopital's rule, last time, second time, we get derivative of the top is negative 2x, derivative of the bottom is secant squared. And that's great because when x is 0, secant squared is 1, so this is 0 over 1, which is just 0 finally. So this whole thing is 0 minus 0, which is just 0. Perfect. So in fact, this whole integral, this original integral, just simplifies to negative this integral. Okay. So now I'm going to erase some of this, and let's carry on. Let me actually box this over here. Perfect. So now how do we handle this integral? So there's a few ways, but the way I kind of thought about it is if this was 2x instead of x, then we can write sine of 2x as 2 sine cosine by trig identity, double angle formula. And then we'll have a product on the inside, so you can take ln of the sum of each of those parts of the product. So a nice fine way of doing that, I think, is to let x be equal to 2u, then dx will be equal to 2 du. Okay, great. Now applying the substitution, a few things happen. It's actually pretty easy to see. So first off, you'll get negative the integral. Well, when x is 0, u is 0, 2 times 0 is 0. When x is pi over 2, u would have to be pi over 4, because 2 times that would be pi over 2. Okay, that's one thing. And then we get ln of sine of 2u, and then dx is, of course, equal to 2 du. So I'll pull the 2 out, actually. So this is negative 2 times that. Good. Okay, what else? Well, okay, so like I said, we're going to use the fact that sine of 2u by a double angle formula is 2 sine of u times cosine of u. And then we'll split this up. Now the next part I think is a pretty unobvious thing. So this splits up, of course, as, that's a pi over 4, ln of 2 plus ln of sine of u plus ln of cosine of u whole du. That's fine. But what's unobvious is that if you focus on this part, because this is pretty easy to deal with, but if you focus on this part, there's a way to rewrite it in terms of this integral over here, and I'll show that right now. So let's kind of just focus on that for a moment. So for right now, let's just focus on the integral from 0 to pi over 4 of ln of sine of u plus ln of cosine of u. Now, what I want to do is I want to attempt to make these look the same, one of them look like the other. Now, at first I wasn't really sure which one to use. I let this be equal to I'm trying to think of, I guess, pi over 2 minus t, because sine of pi over 2 minus t, let me put parentheses on these things. Sine of pi over 2 minus t by identity is just sine of t. I'm sorry, cosine of t. Let me write it here. Sine of pi over 2 minus t, that's cosine of t. And actually the other way around works. This is actually very easy to show. If you have a right triangle, you can kind of see it, right? Because if you have like opposite, adjacent, and hypotenuse, well, if this is theta, then because all angles in triangle add to 180, or pi, this has to be pi over 2 minus theta. So you see that sine of theta is a over c, but cosine of this angle instead is also a over c. And you can say something similar with cosine. So cosine of theta is the same as sine of pi over 2 minus theta as well. But anyways, carrying on with this, if you were to apply this little substitution here, something kind of interesting happens. So for the first integral, this kind of new t integral now, with the first term, becomes ln of sine of pi over 2 minus t, which we just said is cosine of t. And if u is equal to pi over 2 minus t, then what's du is negative dt. The limits change as well. Pi over 2 minus pi over 4 is pi over 4, and pi over 2 minus 0 is pi over 2. And then, of course, you can flip these limits by negating this in the middle, but or this sign. But the issue now is that you kind of double up these. Well, you don't quite double up, but they end up combining. The problem is we want to replicate the original, which involved ln of sine, not ln of cosine. So actually, this thought is a little bit wrong. We want to do this the other way around. So instead of aiming at sine, let's aim at the cosine argument. So now we have the integral from 0 to pi over 4 of ln of sine of u du plus, okay, so let's kind of think about this for a moment. So we get ln of cosine of pi over 2 minus t, which we just said is sine of t. Great. Du is negative dt. The upper limit would be pi over 2 minus pi over 4, which is pi over 4. And the lower limit would be pi over 2 minus 0, which is pi over 2. But you can negate the integrand to switch the limits. So you can make it positive. So again, it's negative because du is equal to negative dt. But if you negate the integral, that swaps the limits. So maybe I should just show what it is before doing that swapping. So you get this, right? And again, that's because it's a pi over 2 on the bottom. And again, that's because if u is equal to pi over 2 minus t, then du is equal to negative dt. But if you switch the limits, that'll negate this back to a positive. This is great because since these limits match, you can combine them back into one, integral from 0 to pi over 2 of ln of sine of, well, these are dummy variables, so just call them x. Do a trivial substitution. U is equal to x for the first one, t is equal to x for the second one, so you get sine of x dx. Which is kind of the original. No, it's not quite the original, but it is kind of like the original. Because the original had a negative in front. Let's just call this I, and let's kind of formulate what we've kind of been glancing over. So our original integral is equal to negative I. So the original integral, 0 to pi over 2, x over tangent of x dx, that's equal to negative what I'm calling I. Okay. That's also equal to, from all of this, negative 2 times the integral from 0 to pi over 4 times ln of 2 du. Okay, that's that. And then minus 2 times the integral from 0 to pi over 4 of the other two. But we notice that that integral from 0 to pi over 4 of the other two, this thing here, that's just equal to I itself. So negative 2 times that integral, which is just I. Now if you focus in on this equation here, and you add this to the other side, you get I. So I is equal to negative 2 times, let's handle this integral really easily. Pull the ln of 2 constant out, then you'll have the integral from 0 to pi over 4 du, which is just the difference between pi over 2 and 0, which is just pi over 2. Okay. Sorry, it's pi over 4. I knew I was missing something. But 2 over 4 is 2, or double pi over 4 is pi over 2, however you want to see it. So it's going to be negative pi over 2 ln of 2, but that's I. But our integral is negative I. So that means the integral from pi over 2 to 0, or 0 to pi over 2, sorry, of x over tangent of x dx is again negative I, which is positive, pi over 2 times ln of 2. Fantastic. And there we go. That was the solution I wanted to share with you. I thought it was kind of interesting. I honestly think the black pen, red pen approach is, well, of course, it's way different. This, I think, is more intuitive. His approach is, I think, a little more clever, honestly. I think it's possibly longer. There are some clever things you see here, of course, with the weird substitutions, and there's a lot of kind of back and forthness. But I encourage you all to watch the video because it's very, very interesting, very cool to see different techniques. But anyways, I hope you all enjoyed this. Please like and subscribe if you can, and I'll see you in the next video. Thanks for watching.